All right, let's dive straight into the fascinating concept of molecular twins. This is a hidden corner of chemistry where molecules share the exact same chemical DNA, but they actually possess entirely different personalities. If you've ever stared at a chemical formula and wondered how it can behave completely differently just based on how it's snapped together, well, you are in the right place. And hey, because chemistry can sometimes feel a bit visually overwhelming, we've specifically designed concepts in this explainer using soft pastel colors. That isn't just for aesthetics, by the way. Using soft mints, peaches, and gentle blues actually reduces cognitive overload, which makes locking in these complex structures a whole lot easier for your brain.
So, here is our roadmap for this explainer. We'll meet the molecular twins, explore the structural isomer family, step into the 3D world, decode easy isomerism, break down the CIP priority rules, and then wrap things up with a handy chemistry exam cheat sheet.
Okay, let's kick things off with Section 1. Meet the molecular twins. Before we get into the really complex 3D stuff, we absolutely have to ground ourselves in the basics of what makes an isomer. Well, an isomer. Think of isomers like buildings made from the exact same pile of bricks, just constructed into completely different shapes. You could have the identical pile of carbon, hydrogen, or oxygen atoms, but depending on the blueprint you use to snap them together, you get an entirely different compound. So, same molecular formula, but a totally different arrangement of atoms.
You can see this perfectly when looking at butane and 2-methylpropane. Both of them share the exact same formula, C4H10. 4 carbons, 10 hydrogens. But their atomic connectivity is entirely different. Butane is the simple straight chain, whereas 2-methylpropane branches off. Same exact ingredients, entirely different structure.
Moving right along to Section 2, the structural isomer family.
Now that we know what isomers are, let's break down the first major category, which is structural isomerism. These isomers fall into 3 distinct buckets, nicely organized here in these calming soft pastel rows. First, we have chain isomers, like our butane example, which just have different arrangements of the carbon chain. Second, position isomers. Here, the functional group stays exactly the same, but it moves around the molecule, like butane 1-ol versus butane 2-ol. And third, functional group isomers. Honestly, this one is wild. Take ethanol, which is an alcohol, and dimethyl ether, which is an ether. They share the exact same formula, C2H6O, but purely because of how they are connected, one is an alcohol and the other is an ether. They behave wildly differently in the real world.
All right, Section 3, entering the 3D world.
So we know structural isomers differ in their 2D connectivity, right? But let's step away from those flat structures for a second. What happens when the structural formula is exactly the same, meaning the atoms are connected in the exact same order, but their spatial arrangement in 3D changes? How does a molecule act when its 3-dimensional geography is physically locked into place?
That brings us to stereoisomers. Same structural formula, totally different spatial arrangement. There are 2 main types you really need to know. First, optical isomers. This happens when you have a chiral carbon atom, which is just a carbon bonded to 4 completely different groups, like in 2-bromobutane. They exist as 2 optical isomers, also known as enantiomers. The second type, and the one we are going to focus heavily on today, is EZ or geometric isomerism. This is caused by a restricted rotation around a carbon-carbon double bond, which gives us isomers like E-butene and Z-butene.
Which leads us straight into Section 4, decoding EZ isomerism.
Let's zero in on this intriguing concept. You might be wondering, what exactly prevents these molecules from just spinning around freely and changing their shape? I mean, single bonds can rotate all day long, so why do these specific molecules get stuck in permanent geometric arrangements?
Well, the secret is in the anatomy of the double bond itself. A double bond isn't just a stronger single bond. It actually consists of 1 sigma bond and 1 pi bond. Think of that pi bond as a locked hinge on a door. It literally prevents free rotation around the carbon-carbon axis. Because it cannot rotate without physically breaking that pi bond, the atomic groups attached to those carbons are permanently locked into their positions in space.
Because they're locked down, we end up with 2 distinct layouts. When we visualize this in a soft mint green, we're looking at the Z isomer. Here is a super easy linguistic mnemonic for you. Z is for zusammen, which is German for together. So the higher priority groups are on the Zane side of the double bond. On the flip side, visualized in a soft peach, is the E isomer. E stands for entgegen, meaning opposite. In this case, those higher priority groups are locked on opposite sides of the double bond.
Let's move on to Section 5, the CIP priority rules.
We keep talking about these groups being on the same or opposite sides, but how do we actually know which groups get higher priority? For that, we use the Cahn Ingold Prelog, or CIP rules. It's a really simple four-step process. Step 1, locate your carbon-carbon double bond. Step 2, compare the two groups attached to the left carbon using their atomic numbers. Step 3, do the exact same thing for the groups on the right carbon. The golden rule here, the atom with the higher atomic number always gets the higher priority. Finally, step 4, just check if those two winning priority groups are on the same side, making it Z, or opposite sides, making it E.
Let's actually walk through this using a real molecule. CHBr equals CHCl. Okay, let's check the left carbon first. It is attached to a bromine and a hydrogen. Bromine has an atomic number of 35, which easily beats hydrogen's atomic number of 1. So bromine takes top priority on the left. Now for the right carbon. It's attached to chlorine and hydrogen. Chlorine's atomic number is 17, again crushing hydrogen's 1. So chlorine gets top priority on the right. Now step back and look at the whole molecule. Are that bromine and that chlorine on the same side of the double bond? If yes, boom, it's a Z isomer. If they're locked on opposite sides, it's an E isomer. Actually, it's incredibly logical when you break it down step by step.
But, and this is a big but, there's a fascinating exception you have to watch out for. I call it the propene trap. Look closely at propene. CH2 equals CH3. The very first carbon in that double bond is attached to two identical hydrogen atoms. Now remember the fundamental condition for EZ isomerism? Each carbon of the double bond must be attached to two different groups. Because propene has two identical hydrogens on one side, you literally can't assign a priority. So it completely fails the conditions for EZ isomerism. There is no E or Z propene. It just doesn't exist.
Finally, Section 6, Chemistry Exam Cheat Sheet.
Let's translate all this spatial chemistry and priority ranking into an actionable, mental checklist for your exams. First, always check for the carbon-carbon double bond. Next, confirm there are two completely different groups per carbon, so you avoid that propene trap we just talked about. Then, assign priority strictly by atomic number. Higher number always equals higher priority. And finally, bring in those mnemonics. Same side is Z for Zusammen, opposite sides is E for Entgegen.
And hey, if you ever need a perfect textbook definition for a test, don't overthink it. Just remember this. EZ isomerism is a type of stereoisomerism that arises because of restricted rotation around a carbon-carbon double bond, resulting in different spatial arrangements of groups attached to the double-bonded carbons. Memorize that exact phrasing, and you are golden.
To wrap up this explainer, I want to leave you with this thought. It really makes you wonder about the microscopic, molecular machinery constantly humming inside us, doesn't it? I mean, if just a single locked pi bond completely changes everything about a simple molecule's physical identity and behavior, imagine the mind-boggling three-dimensional chemical choreography required to build the massive folding proteins and spiraling DNA inside your own body. Every single lock, twist, and turn matters. Thanks so much for joining me on this explainer, and keep exploring the incredible